this guy over here. So that's what I want to talk about next. So that was my sort of 10-minute introduction or so to particle physics, getting us where we are, talking about the Higgs boson. But now the question is, why should you care about the Higgs boson? I'll tell you a little bit of how we discovered it a little later on, but let's talk a little bit about why is it important? Why should you care? Well, one of the reasons would be that if you had this idea, you would have won the Nobel Prize. That's one reason you should care about it. These two gentlemen that you see here, the guy on the left is Francois Angler, and the guy on the right is Peter Higgs, after whom the Higgs boson is named. So you've seen the Higgs already. So I'll actually just read the citation a little bit, and you'll see why. So what they got the Nobel Prize for in 2013, the discovery of the Higgs occurred with the two experiments. It was announced on July 4th of 2012. And in 2013, so very soon after that, they received the Nobel Prize for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which was recently confirmed by the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron Collider. So you might have thought, oh, we discovered it together with our other, the other very large experiment at CERN, which is called CMS. You might have thought maybe we should win the Nobel Prize, but they only give the Nobel Prize to 3 people. But at least we got a shout out over here that without us, the Higgs and Angler would not have received the Nobel Prize, because the Nobel Prize is actually given not just for theory, but a theory that actually follows what nature does. And so until the discovery occurred, they predicted this many, many decades ago. So that's one. The other, this is a little bit of a more complicated side that I would like to have, but I just want to give you a flavor of something, which is how did they come up with this idea? What is this Higgs mechanism? And how did they do it? Well, it dates back a little bit, going back to kind of the mid-1800s, where people were looking at phenomena like electricity and magnetism. Electricity being the stuff that, you know, if you rub your feet on the ground over here on your carpet and it's wintertime, your hair stands on end. Why? Because the charges, the light charges repel each other and your hair loses all its pushing away from it like that. And then magnetism, which is, you know, your refrigerator magnet. And if you have two magnets, depending on how you orient them, they attract each other or repel each other. So those two phenomena at least originally seemed quite distinct from each other, that there were different things. But by about the mid-1800s, particularly as characterized by what was known as Maxwell's equations, he showed that these two phenomena are actually different ways of looking at essentially the same phenomenon. So it was unified in that way. And in these equations, there was this property, and it doesn't matter so much what the name is, called this gauge symmetry, which is these equations exhibited. So some kind of symmetry, sort of a translation that these equations exhibited, that nature looked the same when you made such a symmetry transformation. So if you then took that and you quantized it, so when we learned about quantum mechanics, you could take what was this classical theory and make it quantum mechanical. That goes by the name of quantum electrodynamics, or QED. Then this idea of having this symmetry, the same kind of gauge symmetry, gave rise to a massless particle, which is the gauge boson, and the name gauge boson means it's one of these exchange particles that gives rise to the force, and that particular particle was the photon. So you gave rise to a massless photon. But now if you think back to what I showed you in the previous slide over there, what happens is that, sure, the photon is massless, but there are these W's and Z's that are very massive, 100 times or so the mass of a proton. And so the question then is, how do you kind of keep there's some nice features to this gauge symmetry. How do you keep those features, and yet, because if you keep it exactly that symmetry, you'd end up with something massless. So you have to somehow break the symmetry in some way. And so this idea that there is a broken symmetry is the thing that allows you to say, aha, those elementary particles, the W's and Z's that in our simplest theory would be massless, acquire a mass. And that mechanism by which they acquire the mass is known as the Higgs mechanism. Okay? So that's the sort of more complicated story. Let me give you an analogy of how you might think of the Higgs mass, the Higgs mechanism. So imagine that you're at a cocktail party, and so you guys, filling all of space is the Higgs field, and you are now the Higgs field, right? So standing here in this cocktail party, and into the room walks a particle. In this particular case, it's not drawn terribly well, but that's supposed to be Einstein. So when he walks into this cocktail party, Einstein, what happens? Sort of all of you go, Einstein, wow. And so you all crowd around and want to talk to him and so on. And if you ask how easy is it for Einstein to sort of move through the room, it becomes rather difficult because he's surrounded by all of this Higgs field and interacting with the Higgs field, and so it becomes difficult to go through the room as if he kind of becomes heavier. The different view is I walk into the room, nobody knows who the hell I am, and I can just walk through the room. So, Mr. Einstein, the Einstein particle becomes very heavy because of that interaction with the Higgs field. The Tuts particle remains, fortunately, very light and can go through the room very quickly. So that's kind of the idea. It's the interaction of these particles, these elementary particles, with this Higgs field that we think fills all of space. So right here, right now, is a Higgs field that's filling all of space. So that's the idea, that it's the elementary particles which normally would be massless, but their interaction with the Higgs field gives rise to their mass. Okay, I think I already said that. Oh yeah, let me stretch the analogy a little bit too far. Which is, okay, the particle doesn't walk in, but we're still back at this cocktail party. And instead of Einstein walking into the room, somebody at the edge of the room says, "Psst, Einstein is here." Now, when that happens, all the Higgs field kind of goes, "Oh, what? Einstein's here?" And that rumor propagates through the Higgs field, and it's that kind of oscillation of the Higgs field that is the Higgs boson. Just like an oscillation of an electromagnetic field is the photon. So it's that same idea. So the Higgs boson is this excitation of the Higgs field. Right? So it's the manifestation of the Higgs field, and that's what we look for experimentally. So maybe you're still not convinced that it's important, but because it gives rise to the mass of